Hello, in this lecture we'll be talking about partial derivatives. We're going to generalize partially the idea of a derivative to functions of multiple variables. So think back to calculus, calculus 1, which took place in one dimension along the real number line. And in calculus we spent a lot of time talking about the derivative, right? And so if we had a function that related the variables y, the dependent variable, and the independent variable x, our notation for the derivative was dy dx, and this was the instantaneous rate of change of y with respect to x. Now, the issue that we face in higher dimensions with more than one independent variable is that, in principle, there could be different rates of change, all right? Since there's more than one independent variable, there's more than one direction that you could move, and consequently, perhaps, more than one rate at which the dependent variable could be changing. So we illustrate this very simply with a map of our home state here of Texas, here at SMU. And so, for instance, think about the function describing temperature as a function of latitude and longitude, all right? So as you go, say, east from Dallas, you in general experience very little change in the temperature. Temperature tends to be constant in the east-west direction, although here in the middle of the country the jet stream sort of drops down, but forget about that. Moving east and west, there's generally no change in direction. When you move north, the temperature decreases. So here, if we were talking about a derivative, the derivative with respect to change in, say, x could be close to 0, and the derivative with respect to, say, y, the north-south direction, could be negative. Okay, and so to formalize this idea, we now introduce things called partial derivatives. There are more than one way to travel, and so there's more than one partial derivative. And to indicate this new feature of multivariable space, we have a new symbol, which is simply called the partial symbol. It looks kind of like a backward 6. And here it is. You can call that just really partial. I've heard other notations, but other names for it, but that's usually what I call it. It's just partial. All right, and so we define partial derivatives in exactly the same way that we define regular derivatives through a limit process. So what is the partial derivative with respect to x? Well, you imagine yourself starting at some point xy and then changing x. Okay, so how does that look like in a limit definition? We have the value of a function at some point xy, and then we imagine moving a little bit to the right. Well, what does that look like? It means we're adding a little bit to x, so we have x plus delta x here. And so the difference between those is the finite change with respect to x as we change a little bit of x. So this is the change in the dependent variable, the change in the function f, divided by the change in x. And so we take that limit as delta x goes to 0, and we get what's called the partial derivative with respect to x. Note that y is held constant in this process. Y is the same here as it is here. So y is not changing when we take a partial derivative with respect to x. And if you think about it for a second, that makes sense. I'm interested in change in x. I'm not interested in change in y. And so it makes sense that y remains constant. Similarly, when I define the partial derivative with respect to y, I have my base value here at x comma y, and then I imagine changing y just a little bit. So that produces y plus delta y. My modified value of f, I subtract the original value, that's the change in f, divided by the change in y, delta y, and then we take the limit as delta y goes to 0. Again, note that x does not change in the limit as y goes to 0, as we're evaluating the derivative in y. So x and x are the same value. X is constant when we take partial derivatives with respect to y. So that's really it. That's the limit definition, the fundamental definition of this new object called the partial derivatives. And it's really exactly the same as it was in Calculus 1. The only catch is that you sort of treat any variable that is not the one being considered as a constant. So, how do we compute these things? What I just said is the key to computing these things. In the definition of partial f partial x, y is held constant. in the definition of partial f partial y, x is held constant. And if you can do derivatives back from calculus 1, and you remember the very important fact that the derivative of a constant is 0, I'm going to say that again, the derivative of a constant is always 0, then we can very easily compute partial derivatives, and we'll start with an example. So consider the function x squared plus y. Compute both partial derivatives, change in x, change in y. Well, when I compute the change in x, here I have an x squared, and if x is changing, I take the derivative in x, and that gives me 2x, relatively straightforward. Then I have this plus y. Y is a constant, and the derivative of a constant is 0. So I get no other terms here, I just get 2x. When I compute the derivative with respect to y, I do the same thing. Here I have a y, and the derivative of y is 1. Here I have an x squared, but x is a constant, and so x squared is a constant when I'm taking the derivative with respect to y, and the derivative of a constant is 0, so I get nothing from this term. I simply get the 1 from the y term. So that's a very simple example, function of x plus function of y. Let's do something a little more complicated. F of x, y is x times y squared. Same thing. Derivative with respect to x. Here I have an x times a constant. So I have xy squared, x times a constant. The derivative of x times a constant is 1 times that constant, and here the constant is y squared, and so the derivative with respect to x is y squared. Derivative with respect to y. Here I have a constant times y squared, and the derivative of that is a constant times 2y. Here that constant is x, and so we have 2 times x times y. All right, one more, even more complicated. Hopefully this is enough to sort of see how you get the hang of these things. We'll do more examples in class. F of xy, x times y squared times sine of x squared plus y squared. So it's sort of a combination of the two functions we studied before. This is a product of a function times a function. And then this second term actually has a function of a function, so we're going to have to use chain rule there. But again, when we're taking the derivative with respect to x, we treat this as a function of x times a function of x, which means we have to do a product rule and then a chain rule when we're taking the derivative of the second part. And as long as we treat y like a constant, it's all going to work out. So product rule with respect to x. The derivative of the first term, y squared is a constant, times x. The derivative of that with respect to x is y squared. So there's our y squared. Times the second term, and there's our second term, plus the first term, times the derivative of the second term. Well, now I have to use the chain rule. So the derivative of sine is cosine. And finally, the derivative of the inside with respect to x is 2x. Not 2x plus 1, 2x. So all I did here was I pretended y was a constant, and then I treated it like a calculus 1 ordinary derivative. Now let's do the y term. Derivative of f with respect to y. Derivative of the first, 2xy, times the second, plus the first, times the derivative of the second. Again, chain rule, derivative of sine is cosine, times the derivative of the inside with respect to y, which is 1. So again, I've said it now a number of times. All you have to do is remember that the variable not being differentiated, treat it like a constant, and the derivative of a constant is 0, and you can treat these just like calculus 1 problems. All right, now let's talk a little bit more about partial derivatives before coming back and maybe doing a few more examples. What do these partial derivatives mean? Well, rate of change in a given direction. If in calculus 1, the derivative had the interpretation of the slope of a tangent line, here, the derivative also is the slope of a tangent line, except that in 2 dimensions, there are 2 tangent lines. Really an infinite number, but there are 2 degrees of freedom. There are 2 dimensions, and so you can construct 2 orthogonal tangent lines in the x and y direction. So in this picture here, we have a surface denoted by the function z equals f of xy. And then we have some point, x naught, y naught, and some associated z naught that is obtained by plugging in x naught, y naught into this function. And so that's our point of tangency. The partial derivative with respect to x is the slope of a tangent line that touches that surface at one point here in the x direction. Here in the x direction. And the partial derivative with respect to y is the slope of a tangent line that goes in the y direction and touches that surface at that point, x naught, y naught, z naught. We'll talk in the next lecture about how these two tangent lines can be used to create what's called a tangent plane, but that's the topic of another short lecture. So that's a geometric interpretation. What else can we talk about before we do some more examples? We can, the ideas extend to higher dimensions, okay? So suppose we have a function now of 3 variables, not just 2, but 3. Another great example, we can go back to our drawing at the beginning, is temperature. Temperature varies not only east-west and north-south, but it also varies up-down. And hopefully you know that as you increase the altitude, usually the temperature falls. And so the partial derivative of temperature with respect to z would be negative pretty much anywhere on Earth. So suppose we have some function, f, x, y, and z, x squared times y times z cubed. What's the derivative with respect to x? I hold everything else constant. The derivative of a constant times x squared is 2x times that constant, so we get 2x times yz cubed. Derivative with respect to y, we treat y as a variable, x squared z cubed as a constant, so the derivative of y with respect to y is 1 times that constant, x squared z cubed. We look at the z derivative, x squared y times z cubed. Derivative of z cubed is 3z squared times x squared y, that constant. Again, same game. The more independent variables you have, the more things you have to hold constant when you're taking the derivative of with respect to a given variable. We can even do 4 variables, all right? And then we won't continue this example, but here's something you can imagine: functions that depend on x, y, z, and time. All right? There's plenty of physical things. Again, temperature is a function not only of position but of time. And at say 9 a.m., the derivative of temperature with respect to time is usually positive, unless there's a front moving through or something. So here's a function of 4 variables. Let's take all 4 partial derivatives. Partial derivative with respect to x. Here we have x squared plus a constant over a constant plus a constant. And so the partial derivative with respect to x is 2x plus 0 over that constant, z plus 3, plus 0. So we get this here. Partial derivative with respect to y. A constant plus y over a constant plus a constant. You get 1 over that denominator, 1 over z plus 3. Derivative with respect to z. We have a constant over z plus 3 plus a constant. And so we now have to use the quotient rule, or simply recognize this as being something to the minus 1 power. And so z plus 3 to the minus 1 power is negative z plus 3 to the minus 2 power times that numerator constant, x squared plus y, plus 0 from the t. And finally, partial derivative with respect to t. This whole thing is a constant from t's perspective, and so you just get 1. Finally, let's conclude this lecture by talking about higher order derivatives. You can take multiple derivatives when you are dealing with higher dimensional space, just like you can in one dimension, except as was the case with the first derivative, since there's no longer the derivative, there's also no longer the second derivative, okay? You've got multiple choices in which variable you take the derivative with respect to. And this provides sort of a grid of possible second derivatives. So in 2 dimensions, I've got x and y. I can take the derivative with respect to x twice. So that's the partial derivative with respect to x of the partial derivative with respect to x. We often denote that fxx. You can take the second derivative with respect to y, which is often shorthanded to be fyy. It's the derivative with respect to y of the derivative with respect to y. And then we have what are called mixed partial derivatives. You can take the derivative with respect to y of the derivative with respect to x. In the shorthand notation, you might say f sub x sub y, or simply fxy. That means take x derivative first, then y derivative. Or you could take the y derivative first, followed by the x derivative, and we usually denote that fyx. So here's 4 different second derivatives. As an example, whoops. Here's some simple function again, x squared plus y. If we're asked, it's kind of a textbook type problem, but if we're asked to compute the second derivatives, it usually is useful to first compute the first derivatives. So first we compute the first derivatives. Fx here was 2x, and f sub y was 1. Now, what is the second derivative with respect to x? Well, we have to take the x derivative of f sub x, which gives us 2. What is the y derivative of f sub x? It gives us 0, because 2x is a constant, the derivative of constant 0. What is the y derivative of f sub y? That's 0, and so is the x derivative of f sub y. There's an important point here, but it's more clearly illustrated in a more complicated function. And let's just throw caution to the wind. Let's do second derivatives of a 3-variable function to wrap up this lecture. Here's a function that I made up, x times e to the yz. And let's suppose the problem says compute all second derivatives. Well, now I've got 3 variables. So each of the first derivative can be one of 3, and the second derivative can be one of 3. So we would expect there to be 9 total second derivatives. So let's go ahead and get started. Partial with respect to x, go ahead and compute the first derivatives first. X times a constant, the derivative with respect to x is just going to be that constant, e to the yz. Derivative with respect to y, a constant e to the yz is going to be a constant e to the yz times the derivative of the inside with respect to y, which is x e to the yz times z. A little chain rule there. Derivative with respect to z is going to be exactly the same, constant e to the yz. The derivative of that's going to be constant e to the yz times the derivative with respect to z. So we pick up a y from the chain rule. Now we're ready to compute second derivatives. Second derivative with respect to x, derivative with respect to x of e to the yz. There's no x's here at all, so this is just a constant. The second derivative is 0. The x derivative of fy, we now take the derivative with respect to x. The only x in here is this one, and derivative of x is 1, and so we just get e to the yz times z again. And the derivative with respect to z of fx is going to pull down a y times e to the yz. Oh, so, no, I did that wrong. And that gave away sort of the ultimate point. I have to take the x derivative of fz, which is the x derivative of this thing here, which is just e to the yz times y. All right, now next row, fxy, the y derivative of fx. That is going to pull down a z here, e to the yz times z. The y derivative of fy is, this is a constant, e to the yz. I'm going to get it pull down another z, so x e to the yz times z squared. And the y derivative of fz, again, I'm going to take the y derivative. Now I'm going to have to use the product rule. The derivative of the first is zx e to the yz times the second, which is y. That's this term here. Plus the first times the derivative of the second, that's going to be x e to the yz times 1. So this term here from product rule. All right, last row. Z derivative of fx, that's going to pull down a y. Z derivative of fy, again, I've got 2 terms here. 1, 2, I have to use the product rule. Z derivative of the first is going to pull down a y. X, y, z, e to the yz, I actually wrote it second. The z derivative, then the first times the derivative of the second, gives me just x e to the yz. And finally, z derivative of fz is going to pull down another y. Now, I gave it away earlier by doing the wrong thing when I took the second derivative. You see here that fxy is the same as fyx. And fxz is the same as fzx. And fyz is the same as fzy. So in this example, mixed partial derivatives are equal to each other. It doesn't matter which order you take them in. Actually, that's usually true, unless your function is really bizarre and poorly behaved, like that example we saw in the previous lecture, where you had a point where the limit was different from the two directions. That's kind of like a pathological point, really. It's just a point of non-continuity. So as long as the function is well behaved, the derivatives are continuous, then you can take them in either order. And almost every function we will encounter in this class, except weird special cases like that, has this property. So in general, in science or engineering applications, this is usually true. And this result that mixed derivatives can be taken in any order is known as Clairaut's theorem. So that's it for the lecture. Hope you are coming up with questions, and we'll see you in class.